There are two practical difficulties in using a galvanometer directly for measuring currents. One, for example, if we want to measure current flowing through resistance R in the circuit shown in figure, we connect a galvanometer in series. But then the resistance of the galvanometer is added, which modifies the value of the current. For example, if the resistance of the galvanometer is 100 ohm, then a resistance of 100 ohm is added to the circuit and the current through the circuit will be correspondingly modified. And the galvanometer will not read the desired current correctly. This shows that the device used to measure the current in a circuit should have as low a resistance of its own as possible. Ideally, it should be 0. The other problem associated with using such moving coil galvanometers for measuring normal currents is due to its high sensitivity. These galvanometers are designed to detect weak currents, so even a fraction of an ampere can cause a full-scale deflection, and hence the excess current can damage it. Further, the coil of the wire is usually very thin, and the joule heat I square RT produced in it can melt the wire if a large current passes through it. These problems are taken care of by using a resistance of value less than the resistance of the galvanometer in parallel with the galvanometer. Such a resistance is called shunt. The resistance of the shunt being much smaller than that of the galvanometer, most of the current passes through the shunt and the possibility of damage to the galvanometer is avoided. Further, the shunt and the galvanometer being in parallel, the equivalent resistance of the combination is even lower than the resistance of the shunt. Thus, the above-mentioned difficulties are removed. The device obtained after connecting an appropriate shunt resistance to a galvanometer is calibrated in terms of amperes, milliamperes or microamperes by passing known currents. Such a device is then the ammeter or milliammeter or a microammeter. Determination of the shunt value. Suppose that a galvanometer having its internal resistance G and having a full-scale deflection for a current equal to Ig is to be converted into an ammeter which can measure a current equal to I at full scale. Let the required value of the shunt resistance be S. So, the value of S must be such that the current I divides in such a way that a current Ig flows through the galvanometer and a current Is flows through the shunt, where Is is equal to I minus Ig. The current through the galvanometer is equal to Ig. Current through the shunt is equal to Is. Using Kirchhoff's first law at the junction A, the total current is equal to I is equal to Ig plus Is. From Kirchhoff's second rule, minus Ig into G plus Is into S is equal to 0. Therefore, S is equal to G into Ig upon Is. But Is is equal to I minus Ig. Therefore, S is equal to G into Ig upon I minus Ig.